Hi, in this video, we're going to talk about the history and concepts behind what are known as Taylor and Maclaurin series. And all you need to recall to understand what's going to go on here is how to write a tangent line equation given a curve. So for any curve defined in terms of x and y, you can write the equation of a line tangent to that curve if you have a point, an ordered pair x comma y, and the value of the first derivative at that point, dy dx, or the value for the slope at our given point. Regardless of the type of curve, even if you have to use implicit differentiation, this allows you to model it with a polynomial at that point. But it's a very simple polynomial, it's just a straight line. So visually, the line looks like it matches very well at the point because it matches the slope. And even very close to that point, the line is still very close to the curve. But notice the limitations of a line. As x values get farther away from your tangent point, the line veers farther and farther away from the curve. So it becomes a pretty poor approximation anywhere other than that specific ordered pair x comma y. So enter Brooke Taylor, who was an English mathematician who thought, can I go beyond just a tangent line? And this was right after the time that Newton published many of his ideas on calculus and differentiation. And so Taylor thought, there are plenty of functions that have an infinite number of derivatives, things like trig functions, logarithms, exponentials. And so he thought, instead of just matching up the slope and the first derivative behavior, what if he could match up the behavior of every derivative for a function at a set point? His hypothesis was that he could make a polynomial to approximate a curve that works much better than just a line. So here's how we're going to work through his concept. We're going to let f of x be a function with, let's say, a fifth derivative defined at some point x equals c. And we're going to say that we have known values for every derivative up to the fifth derivative and f of x itself when x equals c. We have our fifth derivative at c, fourth derivative at c, onward, all the way up to f of c. We know all 6 of those values, but we don't necessarily know other values for this function at other values of x. So let's start from the fifth derivative value at c. If we were trying to build the fourth derivative function of x and build it as a polynomial, all we would do is take the antiderivative of this. The antiderivative of a constant would just be that constant times x, but remember, on our antiderivatives, we also have to include an extra constant at the end that might have been there, and we'll still call that capital C. Hopefully not getting that confused with the little c, and I won't be using that anymore throughout the work I'm doing. I'm just using it right now to keep things consistent with what you're used to. Now the only problem with this is, before we move on to the third derivative and on upward trying to get back to that original function, we would prefer to figure out what that constant is at the end. The issue is there's only one function value that we know for the fourth derivative. We know the fourth derivative at c. That's the only way that we can find that constant. So what Taylor came up with, he said, let's design the equation so that at x equals c, we get that our big C, that constant from the antiderivative, equals our fourth derivative value, the value that we know. And the fix to this was, putting more constants into the problem, either adding or subtracting them, is allowed when we take antiderivatives. So he just smartly placed another constant with that x and said, let's write our function as the fifth derivative at c times x minus c, which meant that if we plug c in there, that whole term would zero out. We would get that our antiderivative constant, when we evaluate at c, would be our fourth derivative at little c. Like I was saying, the capital C that I used, I won't have to use anymore. We're going to design this so that every step of the way, we automatically know what the constant is that we're adding into the equation. Using this same process, we could develop that the third derivative, applying power rule all the way across, our first term would now become the fifth derivative over 2 times x minus c to the second. This constant we had from the fourth derivative will now be multiplied by our x minus c plus our third derivative at c, because I've designed something where if I plug in c, it'll zero out these first two terms, and the value for that extra constant has to be the third derivative at c itself. And we're just going to repeat this 3 more times to get back to our original function. But we're going to need a little bit more space because you can see those expressions are going to get a little bit larger. So let's wrap this up and get all the way back to f of x. Here was our third derivative from the previous slide. And so our second derivative, again applying power rule all the way across, we'll have our fifth derivative over 6 times x minus c now to the third power, fourth derivative over 2 times x minus c to the second. The third derivative at c becomes the coefficient on our linear term times x minus c, and our new constant at the end of this one is our second derivative at c. C itself would zero everything out, and we'd be left with that constant value that we stated we knew. First derivative, again, just power rule all the way across, with the new constant at the end being f prime of c. And notice the only thing we really need to start building this up and understand this concept is good knowledge about how to use the power rule for both derivatives, or in this case, for antiderivatives. And we'll go one more step and get our final function. We will get all the way back to saying that if we started off knowing the function and all 5 of these derivatives, knowing their values at x equals c, we have now designed a polynomial that will match all of those values for the function's derivative. And we will get f of x will equal our fifth derivative over 120 times x minus c to the fifth, fourth derivative over 24, x minus c to the fourth, and start to notice the pattern between the derivative number and the power on x. We are third derivative over 6 times x minus c to the third, second derivative over 2 times x minus c to the second power, our first derivative times x minus c really to the first power, and then our f of c, which is not a derivative at all and has no power of x on the end. So if you noticed that pattern of the derivative number matching the power on x, well, there's one more pattern that develops when you take these antiderivatives all the way back to the beginning. Notice the numbers in the denominator: 2, 6, 24, 120. This is a number pattern that we hopefully recognize. These are all of our factorial values. And if we were to go all the way out to the sixth derivative, we would have that one over 720. So I can actually rewrite this function one more time and say that the first one's not just fifth derivative over 120, it's actually the fifth derivative over 5 factorial. The second one is the fourth derivative over 4 factorial, and so on down the line. We've now built in another pattern to show that for each term we actually have 3 things that are matching up: the derivative number, the factorial, and the power on x in every single term. And this was the pattern that Taylor noticed as well. So he asked the question, what if? What if he could generalize this in some way? And he said, what if we could extend this to an infinite number of derivatives and start from the nth derivative at c? Again, like I mentioned at the beginning, there are plenty of functions out there where you can take an infinite number of derivatives. And as long as we could find the value for every derivative at a specific set number, we would be able to make a polynomial with an infinite number of terms to model a function around a point very accurately. Again, moving from a tangent line to a very well-fitting tangent curve. And so what Taylor defined was, given a function f of x with infinitely many derivatives defined at x equals c, the Taylor polynomial is defined as, for the function f of x will be equivalent to the series from 0 to infinity for the nth derivative of c over n factorial times x minus c to the nth power. You could go from 0 to 5 like we did. You can go from 0 to 10. Theoretically, going from 0 to infinity would make something that's 100% equivalent to f of x. And in this form, only one other term to note. That c, when we talk about Taylor polynomials, is referred to as the center. That's where all the action's happening. That's pretty much the same as the tangent point we talked about when we build tangent line equations. And there's one other concept that is a little bit of an offshoot from this. A Scottish mathematician named Colin Maclaurin said, the easiest place to evaluate most functions is at x equals 0. And so he investigated a specific form of Taylor polynomials, all centered at x equals 0. And he said, given a function f of x with infinitely many derivatives defined at x equals 0, the Maclaurin polynomial is defined as the series from 0 to infinity of specifically the nth derivative at 0 over n factorial times x to the n. And notice, not an entirely new concept, it's just a Taylor polynomial with c equal to 0. But it makes calculations on developing these polynomials much easier because 0 is a very friendly value. So that's it for this video, and the only remaining step will actually be building and investigating these Taylor and Maclaurin polynomials. Thank you for watching.